Hello everybody. Today is the last lecture in the course on laser-mat interaction, and today I would like to complete the quantum mechanical description of optical phenomena and explain you what Bloch equations actually mean. So previous lecture we discussed the meaning of the density matrix. So we showed that in particular you can use density matrix in order to explain ensemble of two-level systems. And why we can use density matrix? Well, first of all, we look at an individual two-level system. For each of the two-level systems, we write time-dependent Schrödinger equation, where psi is a wave function that describes two-level system in time. Then, since we are talking about time-dependent Schrödinger equation, the wave function should depend on time, and next to it, it should also depend on coordinates. So dependence on the coordinates sits in this function phi, which are solutions of stationary Schrödinger equation, and dependence on time sits in these coefficients Cn. So if you talk about many level system, that n will show you the number of the level. So if you talk about two-level systems, n can be either 1 or 2. So then if you substitute this linear superposition of wave functions instead of function psi, if you put this linear superposition of wave functions into the time-dependent Schrödinger equations, you will get it in a slightly longer form. So then what you can now do, you can take into account two facts. So if you talk about the product of these wave functions complex conjugate m and wave function n, and if you integrate this over the whole space, if m is equal to n, what we will have to get is 1, because the probability to find a certain particle in the space is 1. It should be equal to 1. And if you talk about two different functions, m is not equal to 1, then since solutions of stationary Schrödinger equation are orthogonal, mutually orthogonal functions by definition, so basically we apply this definition here and show that if m is not equal to n, then this integral should be equal to 0. Then what we do now, we multiply this Schrödinger equation with phi m star, and we integrate both parts of the Schrödinger equation after this multiplication. And what we will get at the end is this form of the Schrödinger equation. And having this form of the Schrödinger equation, further, we can now write this integral in a more simple form. Basically, we can write this in the form of a matrix, where element of the matrix Hmn would be given by this integral. So in terms of matrix, this Schrödinger equation will acquire this form. And if you now take into account the very definition of the density matrix, then we can express this this form of the Schrödinger equation in terms of density matrix. We will get here the sum of products HMK rho Kn minus rho Mk HKn, and this sum is simply the trace of the product of two matrices, and the trace of the product of two matrices is shown by this square parenthesis here. What it actually tells you, that if you use this expression of the trace, it tells you that this expression can be written in a more simple form, in the form like this, that for every element of the density matrix you can expect that its time dependence is equal to a certain element of the trace of the Hamiltonian and the density matrix. Well, we will get what we have here, with that instead of time-dependent Schrödinger equation with a wave function as a variable, we get another time-dependent equation with density matrix as a variable, and this type of Schrödinger equation is called Liouville equation. So if you want to know details of derivation of this equation, so please look in books on quantum mechanics, because it's basically one of the concepts treated in courses on quantum mechanics. What I would like to focus on here is on physics of light-matter interaction. So I take this Liouville equation, I take this form of time-dependent Schrödinger equation for the density matrix in order to understand how light interacts with matter. And I will write as next 3 equations for 3 elements of the density matrix. Diagonal elements of the density matrix rho 1, 1, diagonal elements of the density matrix rho 2, 2, and one of the off-diagonal elements of the density matrix rho 1, 2. Why 1? Because rho 1, 2, according to the definition of the off-diagonal elements of the density matrix, rho 1, 2 should be equal to complex conjugate rho 2, 1. So that's why writing this equation just for one off-diagonal element should be sufficient. So basically you can say that density matrix is Hermitian matrix. That's why we simply write 3 equations instead of 4. Well, what we did, we simply applied this time-dependent equation for the density matrix, and we have written the expressions for each of these 3 elements. And what we have to remember now is that diagonal element of the matrix H is simply the energy of the ground state. Another diagonal element of the density matrix, of the matrix H of the Hamiltonian is the energy of the excited state. And then if you talk about off-diagonal elements of the Hamiltonian, this would be equal to electric field times dipole moment. So what we do here, for simplicity, we assume that dipole moment and electric field are real quantities. That's why we don't need to use sign of complex conjugate here, which would be more general because Hamiltonian is Hermitian matrix too. But here in this particular case, we assume they are real, so this treatment gets a little bit easier. And what we can get now, we can express the very same equations in the form of physical quantities. Instead of abstract H21 and H12, H11 and H22, we will get energies and we will get electric fields and dipole moments. And each dipole moments characterize a particular two-level system. So having all this, we will get 3 equations, as I said already, for 2 diagonal elements of the density matrix and 1 off-diagonal element. And now it is very important to remember again that each of the elements of the density matrix has very clear physical sense, very clear physical meaning. One of the diagonal elements of the density matrix, rho 2, 2, it is basically population of the excited state. Let's call it M. As I showed at the previous lecture, off-diagonal elements of the density matrix, rho 1, 2, practically express polarization of the ensemble of two-level systems. It's not equal to polarization yet, so if you want to find polarization, you have to multiply it by dipole moment and add also to this product complex conjugate of this product. But we know if off-diagonal elements of the density matrix is not equal to 0, it means that ensemble of two-level systems has polarization which is also not equal to 0. So basically the behavior of these off-diagonal elements of the density matrix reflects the behavior of the polarization of the ensemble of two-level systems. And finally, another diagonal element of the density matrix, rho 1, 1, it is a population of the ground state. And if you assume that the total population of two-level system is 1, so that means that population of the ground state will be 1 minus m, 1 minus population of the excited state. So basically what we do here, we assume that number of particles in a two-level system is equal to 1. So it can be either in ground state completely, in the excited state completely, or somewhere in between. And with this, basically we substitute rho 1, 2, rho 2, 2, rho 1, 2, rho 1, 1 with clear expressions, with expressions that have clear physical meaning, polarization and the population of the excited state, and we will get 2 very simple equations. one equation for population of the excited state, and another equation is for polarization of the ensemble of two-level systems. And here, well, first of all, what I would like to emphasize here is that you have to solve these two equations together, of course. And you can see already from here that, for instance, if you look only these two terms, then it will be linear differential equation. So basically, if you neglect this term, then, sorry, if you assume that n is equal to 0, for instance, here, then it would mean that polarization would be a linear function of the electric field, epsilon. But then if you take this population of the excited state into account, then basically polarization can be non-linear function of the electric field, because population of the excited state is also a function of the electric field. So basically these two equations already have in their nature, they already take into account possibility for non-linear optical interaction, for non-linear optical phenomena. So that potentially polarization can be a non-linear function of the electric field, which is shown here by variable epsilon. Then, something missing in these two equations. People realize that something is not very realistic here, because if you simply solve these two equations, it would mean that if you excite two-level systems, ensemble of two-level systems, with electric field epsilon, then you will create some population which will exist forever in the excited state, and you will create some polarization which will oscillate forever as well. It is, as I said already, something very counterintuitive. We know that if in a real system we excite electrons to the excited state, they will sooner or later recombine to the ground state. And also we know that if you excite polarization of ensemble of two-level systems, sooner or later it will damp. And this is one of the effects which we were able to describe with the help of, for instance, a model of linear harmonic oscillator. Yeah? When we excited the harmonic oscillator with a sinusoidal wave, for instance, and we saw that due to damping, if the sinusoidal excitation stops, then polarization will relax in time, will die out, and oscillations will be damped. So basically, in order to take into account this damping, we have to also add additional parameter that describes relaxation in the system. So that means, strictly speaking, if in the case of harmonic oscillator in the very classical oscillator, when we modeled light-matter interaction as interaction of electric field with classical electrons, with classical balls with charge, then there we had just one equation, and in that equation we had a damping term with just one parameter that described damping. If you talk about quantum mechanics, just one parameter to describe damping or describe, so to say, a decay of excitation is not sufficient yet. So you have to introduce two parameters. And one parameter will describe the recombination of the population of the excited state, and another parameter will describe the relaxation of the polarization. Or strictly speaking, one parameter will describe relaxation of the diagonal component of the density matrix, and another parameter will describe relaxation of the off-diagonal component of the density matrix. So basically, what we introduce here, we introduce interaction with the environment. We introduce the fact that two-level systems, ensemble of two-level systems, will interact with the environment, and if you excite ensemble of two-level systems, for instance, with a delta function, with electric field that has a form of delta function, so you will bring electrons into the excited state, and you will induce some polarization. So ensemble of two-level systems will acquire some polarization, and polarization will oscillate in time. But then interacting with environment, interacting with fluctuations of temperature, with cosmic rays, probably interaction with the sound waves, because there is plenty of noise around real object, then electrons will tend to relax to the ground state. Also, each of the two-level systems will tend to interact with the environment, lose its phase, and while acquiring different phase, while each of these two-level systems will acquire different phase, polarization will decay, and this decay will have to be described somehow. In order to describe recombination and decay of polarization, we introduce two parameters, T1 and T2, into this differential equation. So it's an artificial introduction, so it's not something that can be derived theoretically. We just introduce these two parameters to have situation as real as possible, so that's to be as close as possible to the reality. We don't know what behind these parameters. We just have to introduce these terms to account for damping, for account for losses, the similar way as we introduced damping term into equation of harmonic oscillator. And how we should interpret these two parameters, as I said, if you excite ensemble of two-level systems, you bring electrons to the excited state, and the time T1 here will describe the time scale at which electrons will drop down from the ground state to the excited state. And if you excite ensemble of two-level systems, and if vectors which describes wave function for each of the two-level systems in this ensemble, now if these vectors were pointing up in the initial state, and if the excitation, imagine that excitation rotate these vectors over 90 degrees, then since area of these two-level systems will interact with the environment on its own, for instance, it can be scattered. One of the two-level systems will interact with phonon, with a lattice vibration. Another of these two-level systems will catch a cosmic ray. And third two-level system will experience interaction with a free electron which was flying in the neighborhood of these two-level systems. And as a result of all these interactions, which normally are not taken into account in simple models, yeah. So a result of all these interactions, each of these two-level systems will have a phase slip, so will slightly change its phase as a result of the interactions. And if you wait long enough, each of these two-level systems will acquire its own phase, and after a certain moment, vectors which describe wave functions of each of these two-level systems will be pointing randomly somewhere in the plane here in the middle of the Bloch sphere, and it means that if you calculate now polarization of this state, it would be 0. So it's exactly what I want to describe with this term. So this time T2 tells us about the time scale of the relaxation of the polarization which was induced first by the electric field, and if you let now the ensemble of two-level systems evolve on their own, this due to the dephasing between two-level systems, the polarization will be lost, will come to 0, and this time scale of the polarization loss will be described by the time T2. Now, let's do the final step. Let's expand polarization in Taylor series and population of the excited state in Taylor series. We will have terms 0, 1, and 2, and 3 in accordance with the order of all these parameters with respect to electric field of light. So N0, it means that population of the excited state that doesn't depend on the electric field of light. N1 is the population of the excited state which is a linear function of the electric field of light. N2 is the population of the excited state which is a quadratic function with respect to the electric field of light, and so on and so forth. And similarly, we will do with the polarization. P0 is the polarization which doesn't depend on the electric field of light. P1 is the polarization which depends linearly on the electric field of light. P2 is the polarization that depends quadratically on the electric field of light, etc. Now, first of all, the odd terms in the expansion of the population here do not have any physical sense, simply because population cannot be proportional to the electric field of light. Because population should be proportional to the energy. So if you want to bring electron to the excited state, you have to bring some energy to the electron, and the energy is a square of the electric field. It cannot be equal to electric field itself, simply because electric field oscillates in time. Well, so that means that we get rid of all odd terms here, we assume that the initial condition is polarization is equal to 0 and population is equal to 0. Assuming that polarization is equal to 0, basically it says that we can say that we are talking about medium without centrum of symmetry. So popularization of the ground state is 0. So no, medium is centrosymmetric. And for the same reason, if the medium is centrosymmetric, we can also assume that terms, even terms in this expansion of the polarization, which are even with respect to the electric field of light, they must be also 0. And if it is the case, we write three expressions. So those two equations that I showed on the previous slide, we write in the form of three equations, where we first write for P1, we write only terms which are linear with respect to the electric field of light. So it could be term either polarization itself, but then of the first order with respect to electric field of light. Then it should be a term that corresponds to the interaction of electric field and electric dipole. And it will be again term which is proportional to P1, which as we assume, it is linear function with respect to electric field of light. Then we write the expression for the population of the excited state, when we also take terms only quadratic with respect to the electric field of light. And quadratic will give us, for instance, this quadratic behavior would be expressed by the fact that polarization should be proportional to the product of the polarization of the first order times electric field of light which induced this polarization. And then we write the expression for the third polarization of the third order with respect to the electric field of light, and we'll have already an additional term with respect to this very first equation, and this additional term would be proportional to the population of the excited state times electric field of light. So what we do here is writing these two Bloch equations, two equations I wrote on the previous slide. We write them in terms of we write them in a step-like fashion. So instead of looking at the two expressions for polarization and population, which, as I said already, intrinsically nonlinear, we split the nonlinearities in steps. First of all, we calculate polarization induced by the electric field, polarization P1, which is a linear polarization. So basically, we calculate linear optical response. Then we calculate population of the excited state, and the population of the excited state is given by the interaction of the electric field of light and the polarization which this electric field induced in the ensemble of two-level systems. And then polarization of the third order would be given now by the interaction of the electric field of light and population of the excited state, which was created accordingly by the electric field of light and polarization of the first order. So then in this way, we are able to build up three equations that in principle should be sufficient to describe light-matter interaction. Okay, these three expressions are sufficient in fact to describe pump and probe experiment. First of all, what do we do in pump probe experiment? There is a pump pulse that comes that excites carriers from the ground to the excited state. So you create population of the excited state. Population of the excited state is described by this expression. So as we show, it is a function of the electric field and the polarization of the first order. Then there is another pulse coming, the probe pulse, and depending on the population of the excited state, probe pulse sees different transmission through the sample, experiences different transmission through the sample. This different transmission through the sample, which depends on the population of the excited state, is described by this third expression. So, and this is the lowest order in which pump probe experiments can be seen. So in this case, writing these three equations, which are called Bloch equations or optical Bloch equations, writing these three equations, we are able to describe light-matter interaction in the pump and probe experiment. And once again, I would like to emphasize here that these three equations already take into account not only linear optical phenomena, which is in this equation, but also nonlinear optical phenomena. So that means that quantum mechanical approach can intrinsically account for nonlinearities in a medium. So, and eventually it brings me to the conclusions of this lecture. So light-matter interaction can be modeled with the help of optical Bloch equations. The equations do account for nonlinear optical phenomena, and one thing we have to remember here, that in order to make these Bloch equations to bring them closer to the reality, we have to take damping into account. And if damping in classical oscillator was given by one parameter, here we have two parameters which experience decay, and these parameters are population of the excited state, and there is no analogy of this quantity in the model of classical oscillator. So then we had to introduce this population, the relaxation of the population of the excited state T1 in quantum mechanics, and there is also parameter T2, so relaxation of the polarization, which was also described in the case of classical oscillator, in particular by the damping parameter. Here in quantum mechanics it is parameter T2. So with this, let me make the overview of the whole course. So then we started with five main approximations that can help us to describe light-matter interaction: approximation of electric dipole, approximation of continuous medium, linear optical approximation, approximation of isotropic medium, and approximation of no dissipations. And in the following, we were going from one approximation to another and show what we actually overlook that when we accept this approximation, and what kind of parameters have to be added if you want to go beyond this approximation. For instance, in the case of no dissipations, we show that it actually corresponds to the case when entropy doesn't change, there is no damping, so we have equivalence between positive direction of time and negative direction of time. So it means that epsilon, dielectric permittivity that describes linear optical properties of the medium, should be a Hermitian matrix, and it also means that these two parameters which describe damping in the case of quantum mechanical treatment of light-matter interaction, T1 and T2, should be infinitely long. So there is no damping, there is no decay of population of the excited state. And as we now understand, we try to understand this approximation in the lectures 1, 3. Then we went to another approximation of isotropic medium, and try to understand what happens when we go beyond this approximation, when we analyze anisotropy in the medium. Anisotropy in particular can be induced by magnetic field. Anisotropy can be also induced by electric field. Anisotropy can originate from crystal structure of the medium. Then we also analyzed physics beyond linear optical approximation, analyzed phenomena which are called nonlinear optical phenomena, where polarization can be nonlinear function of the electric field of light, when light can interact with light, and frequency of light can change upon interaction with media. And this was the topic of lectures 7 and 8. And finally, the last 4 lectures, we were discussing light-matter interaction in quantum mechanics when we made a transition from classical polarization to quantum dipole moment, when we made a transition from thermodynamic potential to interaction Hamiltonian. And in this way, we were able to describe processes at the level of quantum systems. So since we work still with large number of quantum systems and large number of photons in our experiments, we had to take into account an ensemble of two-level systems. And working with this ensemble, we have suggested the approach based on density matrix. And in this lecture, we also derived so-called optical Bloch equations. And I showed you how to look at the optical Bloch equations, in particular apply them for the description of light-matter interaction in so-called pump and prop experiments. What we have not done, we haven't gone beyond approximation of electric dipole. So everywhere in our lectures, independently whether we used quantum mechanical approach or classical approach or thermodynamic approach, everywhere energy of light-matter interaction was given by the interaction of electric field of light and dipole moment. And basically you can see here it was the core of the whole course. So with this, I think I hope you can have a full picture of what's going on when light interacts with matter, and you can see now we have a good overview of the approximations you can take, and what is very important, although quantum mechanical approximation, quantum mechanical treatment of light-matter interaction is very powerful, it takes into account nonlinear optical effects, but at the same time it's also much more challenging to build up quantum mechanical model for a realistic system. So basically, if you want to treat object that you are working in the lab as an ensemble of two-level systems, there would be too many two-level systems, and then you have to take into account also interaction. You have poorly defined parameters like T1 and T2. At the end is a big question what the value of this model will be. And at the same time, you can have very simple intuitive model in the classical physics and thermodynamics that would be able to predict at least symmetry of the effect that you observe, that will be able to predict qualitative behavior of the effect that you observe, and at least you will be able to say something in advance and then compare, in this case, well, if you use, for instance, very complex simulations using quantum mechanics, compare the outcome of complex quantum mechanical calculations with a relatively simple model. So what I want to say here, it is very important to apply right approximation at the right moment in the right problem. So with this, I would like to conclude the course. Thank you very much and good luck with the further studies. Thank you.